I've had the good fortune of being part of this program for more than a month now, and it's been very productive, especially getting to talk to number theorists who know all kinds of things that I needed to know. Some of that will even come up in this talk. I mean, what happens, everything that you'll see here is joint in a whole lot of different ways. So first of all, I mentioned right here, part of what you'll see is joint with my graduate student, Jason Block, who just finished this past spring and is now in Virginia. And part of it is joint with a number theorist named Debanjana Kundu, fairly young. A few of you might have come across her at some point. And a lot more after that. So let's go on and tell you. First of all, I'm going to start with a picture of the absolute Galois group of the rational numbers. And right away, this is, if not joint, at least I'm taking work from somebody else. This picture essentially was given by Calvert, Harizanov, and Shlapentokh, one of whom is right here, Valentina. I'm adapting it slightly, but they wanted to talk about randomness in this group. That's not where I'm going, but the picture turns out to be very useful. So let's just talk about what's going on here. Sasha, your name is on the slide. What's going on here is that we want to describe the elements of the absolute Galois group of the rational numbers. So that's the Galois group of the algebraic closure of that field over the field itself. And since Q itself is rigid, it's really just the automorphism group of Q bar, the algebraic closure. And we do this just by saying, where can the elements of Q bar go? Right? So, I mean, square root of 2 can be mapped to itself, or it's negative. It's only conjugate over Q. Square root of 3. Whoa. Okay. Yeah, okay, let's just go with this, because you guys understand this pretty well. Square root of 3 has a couple of choices, and it doesn't matter where you sent the square root of 2. When you get to the fourth root of 6 up there, if you're thinking of these as positive reals, this squares to the product of these two, and so where you map it depends on where you map the first two, right? If they were both fixed, this can map to itself or it's negative. But if this product got negated, then you want to pick an imaginary root instead. The point of that is just a tree is the right way to think about this. Your choices at higher levels depend on the choices you made at lower levels. So an automorphism is supposed to be given by a path through this tree. And I see a question already.
So child nodes, like there would be more child nodes in this? Anything square root of any square-free thing, any even square-free thing would also presumably...
Well, I mean, there's no square-free thing in an algebraically closed field.
Or square-free integer, so like square root of 10.
Yeah, I mean, look, in this picture, every element of Q bar will come up here, and quite often there will be situations where you only have one choice. Okay. So there might be places where the tree doesn't even branch, but it certainly will keep on branching as you go up. Okay. Having said that, I'm going to streamline this on the next slide. Okay. So, okay, but, okay, yes. So this is our first picture. Some of you may already be thinking of work by Cherlin, Vandendries, and McIntyre, one of whom is here, on this general topic. So they were not really coming at it from a computability point of view, and so I'm going to go in different directions, but there's very useful stuff there. And some of you might be thinking of work by Downey and Melnikov, who are both in New Zealand, and so they get a pass from coming to this conference. But they came at this from the point of view of topological groups. They are computability people, but they were doing computable topology and wanted to have a group structure. So there's a whole lot of ways of looking at this. Yeah. Okay. Excellent. Yes. I wasn't there, but yes. But you know, you can come at this from a lot of ways. But the tree structure is a very natural way to go about it. I promised to streamline it a little bit. So let's maybe think of Q bar as being given by a tower of finite Galois extensions in an effective way. And if you name a primitive generator of each extension, then okay, the tree is going to look pretty much the same, but we can just say primitive generator goes to one of its conjugates. In this case, it looks like Z1 had degree 2, Z2 had degree 2 over Z1, so degree 4 conjugates in total. After that, I think the next one, I'm not telling you what these Z's are, but primitive generators in whatever tower you came up with. And that sort of makes it a little bit nicer because now the nodes at a given level really are the elements of the finite Galois group of that Kn at that level, right? I mean, where do you send a primitive generator? That tells you everything about that automorphism of Kn. Okay? And point here, again, I'm coming from computable structure theory. I want not just to give a list of the elements of the group, but I want to be able to do the group operations on them. And there are continuum many of those elements. So this is not your normal computable group where the domain can be made into the natural numbers. But we can do this effectively. The point is you have to use Turing functionals, right? So Oracle Turing programs, where you give the program, if you're trying to compute the group operation, let's say, you give the program two paths as oracles, right? They're infinite objects, but that's exactly what an oracle is supposed to be, okay? And the Turing functional with those two oracles combined together into a single one, that's the little O plus notation there, with those two oracles should compute their composition, which you certainly can do. It's totally effective. Computing the inverse also, same way. But just to be clear here, the paths, the f and the g, don't have to be computable, right? This is a very discrete oracle Turing function. How you got those oracles is your business. It just takes them and computes the composition. And that is an effective operation, even if the paths were not computable. Okay. So far so good. Questions are always welcome. So now I want to talk about the absolute Galois group of Q in the end here, and so does everybody else, but we're going to take one slide and just talk about a slightly more general setting and point out that the tree for the absolute Galois group of Q is actually pretty nice compared to a lot of other situations. We're also going to spend a little time on simpler Galois groups. I mean, part of the point here is doing computability on the absolute Galois group. We'd like to try to quantify the notion that the absolute Galois group of Q is really nasty, right? It has this reputation. People feel like, oh, we don't understand anything about it. We don't even know many automorphisms. Let's try to quantify that by the end of this talk. Okay, so first of all, just ways in which it's nice. If you were trying to do this just in general for a field extension, E of a ground field F, so let's name the element, these are countable fields still. Let's name the elements of E just by x1, x2, x3. Okay, so same thing. You would try to say where should x0 map? And ideally, well, the obvious targets would be conjugates of x0 over f. Once you've sent it somewhere, you would say where does x1 map? And now, if x0 got fixed, of course, then look for the minimal polynomial of x1 over f of x0. If x0 got mapped to something else, then you have to do a little work to figure out what minimal polynomial you should be aiming for with x1, but that's effective. And so you would get a tree that looks much like the one before, but it's not as nice in general. Now, it is still true that the automorphisms of E that fix f pointwise will be precisely the paths through this tree, if we do it right. I haven't done every detail here. And since, if we're assuming the extension is algebraic, then there will be only finitely many nodes at each level. Now, that might take a little bit of thought. I mean, how do you actually know what are the conjugates of x0? Well, you don't necessarily. If f is somewhat intractable, it's not always easy to find the minimal polynomial of x0 over the ground field f. What you can do, though, is find some polynomial for which x0 is a root, start listing out the roots of that polynomial in E, which seem like potential conjugates, there will only be finitely many even of those, and eventually maybe you realize that the thing you thought was the minimal polynomial factors in some way, and so you sort of, you don't cross off nodes from the tree, but you don't extend them any further. So they die and they don't give you any automorphisms. Okay, if you had a splitting algorithm for F, not sure everybody knows what that means. That means if you can decide which polynomials over the field F are irreducible there, okay? Which is not always the case. It is the case for Q, it's the case for the fields we'll deal with for the rest of the day, but I want to make the point. Even that is an assumption, right? Assuming you have a splitting algorithm, you can figure out precisely what the conjugates of X0 are, and in fact, you could also make sure that you don't map anything in F to anything other than itself, okay? If you want to know how many nodes there are at a given level, so if you want to compute the branching, a splitting algorithm for the bigger field E would give you that, right? Once you know the minimal polynomial of X0, you want to say how many other elements of E satisfy this polynomial. In the case of the algebraic closure, this is obvious, but for fields in general, not so obvious, right? And, okay. And last thing, the tree we had for Q had no dead-end nodes whatsoever. I mean, that's a really nice tree that way. Every node is extendable. Here, if you want that, that needs more than just splitting algorithms. I mean, that actually requires what we computable structure theorists would call relative computable categoricity. And I'm not going to go anywhere with that, but if that's something you know about, feel free to think about that connection, think about automorphism groups of structures, computable structures in general, and put that together. Okay. With that, back to nicer Galois groups. Most of what we do from here out will be Galois groups of an algebraic closure over a ground field. Okay. Man, there's a tree on every slide here so far, right? Well, that's how you should be thinking. You know, we're talking about continuum-sized groups, and looking at them as paths through trees is the natural, effective way to go about it. Okay, so if you're starting with a finite field, okay, we know a lot about those absolute Galois groups. They're always isomorphic to Z hat, the profinite completion of the additive group of Z. And in turn, Z hat is this direct product of the additive groups of p-adic integers across all primes P. And the ZP pluses, right, these smaller groups here, are given very, very naturally by trees, right? So a p-adic integer just consists of a string of integers. The nth one should be less than p to the n, down to 0. And each one should be, so for instance here, if you start with p minus 1, the next thing in your sequence should be congruent to p minus 1 mod p. Okay, so p minus 1 itself, or 2p minus 1, 3p minus 1, up to p squared minus 1. The next one after that should be congruent to this one, mod p squared, and so on up. Totally natural setup for a tree, right? So the p-adic integers are the path through this tree. Addition is component-wise modulo pn for the level n. So that's totally effective. Taking inverses is effective. This is a computable tree presentation of this group in the same sense we were talking about before. Okay. And there, okay. So what about that? Let's just deal with this one first. This is not the actual Galois group I was talking about. It is a Galois group, but anyway. So looking at those paths, there are a continuum many of those paths. Some of them are themselves computable, right? I mean, if somebody asks you for the identity path, that's totally easy. 0, 0, 0, 0. I can compute that. There are a lot of computable paths, but only countably many. So it's actually a pretty small subgroup. Natural question to ask, how much does that subgroup resemble the big group? And there's a fairly quick answer to that. So Jason Block, the student I mentioned, took work of Vanda Shmilev from a good 70 years ago now, and used it to show that, in fact, the computable automorphisms, well, the computable elements of ZP+, let's say, form an elementary subgroup. Okay, elementary subgroup, that means if you look at elements of the small group, the first order theory of the big group relative to those elements is exactly the same as the first order theory of the small group. Okay, we'll be talking about that sort of thing more as we go, but in this case it works out perfectly nicely. In fact, everything about this group is really nice and easy. Okay, so simple existential formulas. So let's actually, the formula I have in mind here is down in the last paragraph here. There exists a G such that B times G equals some combination of some parameters Fi. Okay, if somebody gives you a tuple of parameters, obvious question, is that formula true or not for those parameters? Okay, so while you think about that, there's a question.
What's the degree of an element of ZP plus?
Okay, so an element of ZP plus is a path through the tree, and degree means Turing degree.
Oh.
Right, is it computable or not?
Oh, okay.
Right, okay, yes, I'm sorry. With this audience, I should make that clear. Where did that come up exactly? End of the first.
I is a Turing ideal.
Yeah, oh, okay. So the degree of the element should be an I. That makes sense, right? The Turing degree should be in this Turing ideal. Okay. If you're not familiar with Turing ideals, just think of everything computable from a given degree. That would be a principal Turing ideal, something like that. Okay. So answers, I mean, the answer is right on the board there on the slides. If you're trying to figure out whether a given tuple of f satisfies this equation, it's actually totally easy. The criterion, which is right up here, is simply, okay, assuming b is not 0, so this statement is not trivial, go and find the highest power of p, the specific p we're dealing with here, highest power that divides b, and then check whether that power divides the other side of the equation, which you can do using just finitely much of the oracle. Just go up to that level in each path, right? Multiply by AI, add them up, and see if it's divisible by PE. See if you get 0 in that level. Okay? And so that's decidable. And in fact, if you start taking more interesting existential formulas, put them together, still decidable. Stick on more quantifiers at the front. I mean, you're actually defining here a Clopin set in the tree, just a finite union of sets above specific nodes at this one level E. And so it turns out you can decide formulas with even more quantifiers for these parameters. I mean, this is, for computable structure theorists, this is a really nice structure. Some would say a really boring structure, but it seems like everything is good here. It's not quite perfect, though. And so I need to take a minute and just remind everybody about terminology. The words computable and decidable. In almost all contexts, we use those interchangeably. Right? I mean, if I were going to make a distinction, sometimes I say a function is computable and a set is decidable. But the set is decidable if and only if its characteristic function is computable, right? So we just plug these words in and out, except in computable structure theory. And I don't quite know how this happened. It was before my time. It's not my fault. But in computable structure theory, a computable, so back in the good old situation where the domain is the natural numbers, a computable structure is a structure whose atomic diagram can be decided. So you can decide all the addition, multiplication, whatever operations you have, you can compute. You can decide the relations, if there are any, in the structure. A decidable structure is one where the elementary diagram is decidable. And I don't think there was any rhyme or reason for why it was set up that way, but those are the terms everybody uses. Okay, so we got to live with it at this point. Yeah, I mean, look, if I were my advisor, I might go on a campaign to straighten this out, but I'm not. Those of you who know him, you get it. Okay, in any case, this is the situation. And it looks as though ZP plus is sort of the continuum-sized analog of a decidable structure here. I mean, it seems like you can decide everything about about the individual elements of the structure. I mean, we've known for a long time that the theory of even the ring ZP is decidable, but this is more than that, right? This is the entire diagram. Okay, so why aren't we there?
In Russian, it's clear. It's constructive and strongly constructive. So.
Okay, yeah, there you know which is which. Okay, so, well, as I say, we could try to change that, but I'm not up for it. Not the place to discuss it, okay? Yeah, all right, so I'm trying to go forwards here. Here's the problem. With a continuum size structure, what I said at the beginning was we can compute the two group operations, including inversion as one of them. Inversion does not come automatically from composition in this context. What we can't do is decide whether two paths are equal. The most basic thing, right? Here are two paths. Are they the same, right? Well, okay, I can start checking. I mean, they're the same at level 1. Give me the paths as oracles. Same at level 1, yeah. Same at level 2, yeah. If they're not equal, I'll realize it at some point. You know, I'll see the two paths diverge. But if they are equal, well, I'll never really be sure. All I can say is they're the same at the first umpty-ump million levels. Huh. So this is frustrating, right? I mean, this is not how it's supposed to work. How it's supposed to work is things with quantifiers are hard. Atomic formulas are easy. And this structure just has that backwards, right? You can try to say something like, oh, every formula with quantifiers is decidable. You have to be a little more careful than that, because here's a really stupid formula with quantifiers. It's equivalent to a quantifier free, so you'd have to say something about properly existential formulas are decidable. You can do that. The definition that Jason Block and I came up with to try to deal with this situation is the following here. So I'm calling the presentation of ZP plus that we have a decidable tree presentation, which means, okay, so everything that we've said so far, you know, the group operations are decidable on paths through a computable tree. And the elementary diagram can be decided in the following sense. So there's a Turing functional which accepts as input, first of all, a formula, fine. I'll give the formula with n free variables, but then give me n paths through the tree as oracles, right? That's how you have to give them. So you tell me which elements of the structure you're asking about for this formula alpha. And then the other thing you have to give me is the atomic diagram of the substructure generated by those elements. Just thinking of those elements now as individual constants. So the substructure they generate is a countable substructure, certainly. And this is saying then, if, for instance, if x1 equals x4 in this particular tuple, and the functional is allowed to ask, if it finds it needs to know this, it can ask, hey, does x1 equal x4? And this last thing in the diagram, in the oracle here, the atomic diagram answers that question. And not just does x1 equal x4, but if you're trying to be really sneaky and slip in something like this, if the functional is smart enough to say, hey, does x2 to the 612th power equal x1 to the 493rd? The diagram has to fess up and say, okay, yes, I was trying to pull something here, you got me, yes, they're equal. Okay? So with that information, you're supposed to be able to decide truth of the formula for those particular elements. So that's tree decidability, a decidable tree presentation. In a structure of size continuum, it's as close as you're going to get to what we always called a decidable structure, right? Because with continuum many elements, there's just no way they can all be identified by finite strings from a countable alphabet. So, okay, and so, okay, so objection, this is not really computable in the usual sense, because how are you supposed to give that diagram? Answer, well, what we're trying to say is this structure is as simple as possible for something of size continuum. Okay? Everything else about it is decidable. Equality, yes, it's a problem, but that's normal. And with this definition, first of all, the tree that the p branching tree that I gave you for ZP plus is a decidable tree presentation of that group. Second of all, coming back to Z hat, okay, so remember Z hat is just the product, Z hat plus, the additive group, is the product of all the ZP pluses. And it's quite easy to take all those countably many trees for each different p and sort of splice the levels together, just dovetailing, and get a single tree for ZP plus, whose elements are omega tuples from that product. Okay. And with that, it does turn out that you get a decidable tree presentation of ZP plus even. Okay. Now, you might have a few doubts about that when you take this infinite product here. For instance, this is not a full proof by any means, but to explain the thing that jumps out at one, if I've got an existential formula, okay, so here's a fairly simple one. X is divisible by 84 in this group, true of some x's, false of others. You give me an oracle for x. Well, the oracle for x sort of decomposes into an x sub p from every ZP plus, and it seems like all of them have to satisfy the existential in order for this existential statement to be true in Z hat plus. That's a lot of stuff to check. That doesn't sound decidable, but it works out because remember how it works. ZP plus realizes this formula if and only if, well, you went and found the highest power of p that divided 84. Well, there's only 3 primes for which that's anything bigger than 0. And when it is 0, the function is true trivial. The existential is true trivially. So you just have to check, okay, the prime factors to their powers are 4, 3, and 7. Look at x, take it down to Z2 plus and check the second level, Z3 plus, check the first level, Z7 plus, check the first level, add them up. And yeah, nothing to add up, just check them. And if all of them are 0 at that level, then this statement is true, and if not, then it isn't. Right? So somehow, even in this infinite product, you still have this tree decidability. Okay, that's not a proof for, pi 17 formulas, okay, so I'm not going to go any further than that here. But it turns out, yes, ZP plus, which I'll remind you is the absolute Galois group of any finite field, is tree decidable in this way. So there are good absolute Galois groups out there. Very nice ones that not only that we know what they are up to isomorphism, but we can really decide all kinds of stuff about them in a computability theoretic sense. Okay, okay, the cyclotomic field, we might as well touch on that while we're here. Touch on it because its Galois group is similar to what's been going on. There you get the multiplicative subgroup of the ring Z hat, so all the units in the ring. The ring works just like you think it should. And it's decidable whether something is it's decidable in ZP cross whether something is a unit or not. So you can indeed make a computable tree where the paths are precisely the elements of Z cross, Z hat cross there. Okay. And how nice is that? I mean, maybe it's still tree decidable. Now it isn't. Okay. And so can you figure out whether an element is divisible by 2? Okay, so once again, I'm going to let you think about that while I answer a question.
This is the multiplicative groups of units in Z hat. So is it ZP, is it the product of ZP plus?
So here it's the product of all the ZP crosses, the multiplicative subgroup of the ring ZP.
Oh.
Okay. However, here, let me go ahead. And point out, each ZP cross in turn looks kind of like an additive group.
Oh,
ZP cross is the product of ZP plus with this finite group Z mod P minus 1 Z, the additive,
Okay.
cyclic group of order P minus 1.
Cross canceled the plus.
Yeah, okay. And so up here, this is now being written multiplicatively, but it's the same question, divisibility by 2 in the group. Now here, I want to know if an element up here was divisible by 2, down here this, you're sort of thinking of it additively. For every odd, by the way, 2 is a little bit different here. 2 is weird, but it's not hard, it's just different. But for odd primes P, this is ZP cross. P minus 1 is always even, always divisible by 2. That means that in Z mod P minus 1Z, half the elements are, the even elements are squares, right? In Z mod 6, the squares, the things divisible by 2 are just 0, 2, and 4. The other 3 aren't. And if you've got an X, and you want to know if it's divisible by 2, it needs to be even in every one of those Z P minus 1Z plus factors. That's infinitely much stuff to check. So that's only a pi 0, 1 fact. Okay, it's not something you can just take the oracle and look at finitely much and decide. Okay, so this is not a tree-decidable structure anymore. This one's a little more complicated. Still pretty nice. So let's see. Yes? Yes. Did he just say pi 0, 1 for an existentially defined set? What's with that? Huh? Okay, wait, I mean, that it's not supposed to work that way, right? I mean, for a computable structure theorist, existential sets define, sigma 1 stuff. It's an existential, for God's sake, that's how it's supposed to work. So what's going on here? Well, we're talking about paths through a tree. An existentially defined set, the existential is quantifying over those paths, which means it's a second order quantifier. So if you're just looking at the set, I have it up there, right? Looking at this set, existentially defined, on its face, all you know is that that thing is sigma 1, 1. So does everybody know this hierarchy? First order quantifiers, you're just quantifying over natural numbers. Those are the ones where people call it sigma 0, 1 or pi 0, 6 or whatever. Sigma 1, 1 means you have an existential second order quantifier. And that's basically, compared to first order quantifiers, that's off the charts difficult. I mean, all the first order quantifiers together, going through ordinals and stuff, just barely get up to sigma 1. Well, never mind, let's not go there. It's way up. But that doesn't mean that this set, where am I? Yeah, there. Doesn't mean that this set is really that hard. That's just the way it's defined in this definition. Maybe it has a simpler definition. And in this case, it does. I mean, when we were talking about divisibility by 2 just now, it actually is pi 0, 1, right? The element of z hat cross had to have even numbers in these infinitely many spots. Okay, so deal with it. Sorry, folks. If it makes you feel any better, when you throw in negations, it's no longer pi 0, 1. If you have an existential formula, but the alpha that the quantifier free part has negations as well as positive equations, then satisfying it is a sigma 0, 2 property. You have to find a spot where the negations are true of your paths and then say, now I need the positive part, the equations, to stay true in one way or another at every level up from there. So there is a node such that at all levels above this, the right thing happens. Sigma 0, 2. And incidentally, that's very much based on the fact that the trees we're looking at are finite branching. Okay, if they weren't, then things get much, much harder. So, okay. So yeah, it can be as bad as sigma 0, 2. Jason showed that as well. Okay, I want to do one other idea from computable structure theory. on these groups, and then we'll move into absolute Galois group of Q. So this idea, these generalized Skolem functions. Here's the deal. In computable structure theory, if you've got a computable structure, just computable, so all you know is how to compute the atomic diagram. But if somebody says, here's an existential sentence that I promise you is true, there exists an X such that something happens, you can just go through the structure and search for an X where it happens, right? I mean, just like searching for the root of a polynomial, if you know that it has a root. You'll find it sooner or later, and you'll realize that you'll find it because the atomic diagram is decidable, and you'll see, aha, this works. I've got my witness. It might not be the only X that works. If you're going through the natural numbers, you probably do them in order. You find the least one in that ordering that works. But anyway, you can find a witness. Okay. When you're given the path through a tree, in general, it ain't that easy, right? I mean, how are you going to go through entire paths and decide whether they satisfy an atomic formula? So it would be that, saying that it would be that easy, that it is that easy, would mean saying that we can compute what I'm calling here a generalized Skolem function. So a Skolem function for a particular formula that begins with an existential says, okay, for this formula, with some tuple with arbitrary tuple of parameters from the structure, so this A vec tuple of parameters from the structure A, give me the paths representing A, and I will produce a witness to this formula if one exists. Okay, now, okay, there are such functions just by the axiom of choice, but can you compute one? Interesting question. The answer is not, first of all, the answer is not always. As a matter of fact, I'm even allowing alpha here to have more quantifiers, in which case you'd certainly think not always. In some cases, yes. Just to be clear about the rules, you give the function s any tuple of parameters that you want from the structure, but if the tuple does not if there is no witness for this tuple, then the computable function can do whatever it wants. I mean, you give it garbage, it can give you back garbage, or never halt, or whatever. So only if you give it a tuple A that satisfies this, does it have to work and give you back a witness. Okay. So this would be the same as the situation in countable computable structure theory if you can compute these Skolem functions, at least for existential formulas. Yeah.
What does it really mean to compute something with a Turing functional when our A bars need not be computable themselves? Are we feeding the Turing functional?
Yeah. Just like on the very first slide, right? You can give the functional a tuple of parameters, and the functional just minds its own business and says, okay, if you give me something non-computable, I don't know how you got it, but that's your problem. Okay. Yeah. So it should work for every tuple of parameters. The witness it computes will always be computable from the parameters, if there is a computable Skolem function. Okay. So just a summary of where you can do this and where you can't. As long as we're leaving out disjunctions, you can compute Skolem functions in ZP+. You can compute them in Z hat plus, the product. Not surprising, you can do it for each individual component. You can, hang on, there. Okay, yeah, yep. Okay, now if I do this too much, it's going to go all the way back to the beginning. Okay, the next slide says on to gal of Q, so now you're interested. But yeah, we were right here in Z hat cross, you can compute Skolem functions. You can't decide whether the formula is true or not. You can't decide whether the tuple has a witness, but you can say if there is a witness, it's got to start like this, and it's got to keep going like this. And if there really is a witness, you can compute that witness. Okay, so these are sort of orthogonal to each other, Skolem functions and deciding the diagram that way. I haven't talked at all about the tree presentations of the real numbers and the complex numbers. They do exist, modulo one little tweak from what we've been doing. In the real numbers, there are not always computable Skolem functions. They could be computed if you did the same trick of saying you have to give me the atomic diagram. But without that, sometimes you can't compute Skolem functions in the field of real numbers. In the complex numbers, they're just not computable, period. I mean, really, really simple formulas, okay, yes. But in general, there are no computable Skolem functions for the complex numbers, which is weird. I'm not going to go there at all in this talk, but do feel free to ask later on if you want to know. What about the absolute Galois group of Q? Okay. Last word before we start on that. Disjunctions make things harder. In a disjunction, it can be that the Skolem function, if you're trying to compute a witness, you don't know which of the two disjuncts is true, and you could compute a witness for either one if it's true, but you don't know which one to compute. So disjunctions are bad news for Skolem functions, and we usually just stay away from that and say, conjunctions of equations and equations, and then existential or maybe even more quantifiers than that. Okay. All right. So, yes, doing this very gently now. Okay. Absolute Galois group of Q. Okay. So what about this? You saw the tree presentation way back on slide number 3, I guess. Here's a very basic formula. Existential says that, okay, F is some path through this tree, some automorphism of Q bar. Is it, in the Galois group, is it divisible by 2? I'm writing this multiplicatively, so, or, with composition, but so to speak, does it have a square root in the Galois group? Okay, some elements do, some elements don't. Sure. So, okay, well, here, okay, quick survey. I think there are more people on this side. I'm going to draw this over here. I want to show you sort of dynamically what you're going to do here. Let us say, for the sake of argument here, it's going to be helpful that our first field in that tower that unions up to Q bar, our first field is generated by the square root of 5. Somebody's giving me an F. I want to know what are the possible square roots of F. Now, if F itself isn't a square, then I don't care. So if F is a square, then no matter what its square roots are, at this level, F has to send square root of 5 to square root of 5. And both of these two things, right, root 5 and negative root 5, so far look like they could be square roots of F. Right? Both of those automorphisms would work. Okay, and so the tree is possible G with G composed with G equals F. F is being given to us by an oracle, so we can look it up as we go. Just to put something random in at the next level, let us say K2 is something whose Galois group over K1 is S3. And let us say, okay, so F here was the identity. F here needs to be a square, and it turns out it's still the identity. Okay, in S3 there are 4 things that square to the identity. There are 6 elements. 4 of them square to the identity, the other 2 square to each other. So far, I'm not going to name them, but for each of these there are 4 possibilities. Okay. If you see what's going on here, the paths through this tree will be the automorphisms that square to F. I mean, if there are none of them at all, then there will be some level where the tree just is empty. The tree will be finite. Okay, if the tree is infinite, there will be a square root. And, Okay, which means, again, the property of having a square root is pi 0, 1. Tree, tree has to have a node at every level. Yeah, okay. So we're asking, so first of all, we're asking, is there a path? And interesting question, could we compute a path from this f? I mean, if f were computable, does the tree have a computable path? More generally, how do we come up with a path if somebody is giving us f? Okay, so the next level, interesting stuff happens. K3 is generated over K2, let us say, by a fifth root of unity. So primitive fifth root of unity. Okay. The Galois group of this over this is the cyclic group of 4 elements. K3 over K2 is, I'll just call it C4, cyclic group of 4 elements. K3 over Q, it's something bigger, of course, but basically looking at this. Okay, so anything? Yeah, okay, so if I'm being really careful, I would probably call this a primitive generator rather than zeta 5. That's the way we did it the first time around. But yeah, the interesting thing here is that. Okay, I see. Yes. And if I say over Q, then it's got, okay, so if I say over Q, then there's that S3 mixed in. Which if we do it right will just be a product, but okay. What I'm interested in is the C4 part. So let's leave it at this. Let's look at what happens here. Okay. Primitive fifth root, zeta 5. I just mentioned, and you know, zeta 5 generates the square root of 5, right? And you can look at the elements. So okay, instead of talking about this guy, let's just say, what can happen to zeta 5? It can be mapped to itself, its square, its cube, its fourth power. That's where you get the Z4. In that group, there are 2 squares. I mean, if you're doing it additively, the 0 and the 2. Okay, they're identity and complex conjugation on this. First possibility here, if your f maps zeta 5 to zeta 5, then you can figure out from that what the square roots are. They're either the identity or the 2, the complex conjugation. And it turns out both of those map square root of 5 to itself. Okay, so I was saying here what f was. Now we look here and we find, let us say, that f of zeta 5. If we find that f of zeta 5 equals zeta 5, then the g has to be here, right? There are still 2 different things it could be, but the tree does this, and that half just dies off. Okay. On the other hand, if f of zeta 5 was the other square, the complex conjugate, then it turns out that these nodes all extend and those all die. Okay, so which is it? Well, you go to your f oracle and you say, okay, what is f of zeta 5? And you get an answer. And once you've got that answer, you're able to compute the square root here, at least. Not all the way up here yet, but at least you know at the first level which way g should go. So there's a hope that we could compute g, a square root of f, just from f itself. Okay, a hope. Well, okay, so does this always work? I mean, what about the square root of 2? If you try the same thing and you look at the geometry and you say, oh, zeta 8 generates the square root of 2, so let's try that. You do that. Zeta 8 has 3 other conjugates plus itself over q. All 4 of those maps square to the identity. And so in that case, well, f must be the identity, and that doesn't tell you any, and all 4 g's all 4 possibilities squared at that. It doesn't tell you anything about what you should do, what the square root has to do to the square root of 2. Square root, square root. This is getting confusing, but okay. So, well, all right, so maybe zeta 8 wasn't the right thing to try. It turns out there is something you can try that will tell you what to do with the square root of 2. I think the 4th root does it, or square root of 2 minus root 2 will do it. You know, if you know f there, you can figure out g of the square root of 2. If we were doing the square root of 7, we don't know if there's any way. Okay. You might think about trying to realize C4 over the square root of 7, but there's a fairly early theorem in Galois theory that says over Q, you can't do that. 7 is not a, 7 is not a sum of squares, right? So, okay, but maybe maybe there's some other way to determine it, right? Just like there was with the square root of 2. So just in the last couple of weeks, Bjorn Poonen came up with a proof that if you're looking at an S3 situation here, there will eventually be a way to tell whether G should go to the identity or not, but the other 3 things will never be distinguished anywhere higher up in the tree. And the reason is purely group theoretic. There just isn't a group that can do it. Okay. I had no prayer of doing this proof myself, by the way. I mean, I totally needed this program to come up with anything like that. So we've got interesting stuff here. Hang on. I do have a partial answer to the question, though, which is, and this actually came before this program. This was joint with the person I mentioned, Debanjana Kundu. There is no computable Skolem function in Galois group of Q for this particular formula, saying that f is a square. Okay? And so here's the proof. Suppose you had one. You know, some bright student comes in with a Turing functional and says, I think this computes square roots in the Galois group. So instead of just saying, well, you're wrong, there's a theorem, of course, you give the student a chance. You say, okay, well, tell me what your functional does on the identity, which is a square. So it should output something, right? And so the functional runs on the identity. Now, of course, it slowly produces an automorphism of Q bar. If it does anything crazy, then okay, it's wrong. But what we're looking for is run that function until it gives you some sort of value on the input I, the square root of -1, right? If you're looking for automorphisms that square to the identity, well, the identity itself is a possibility. Complex conjugation or conjugates thereof are the other possibilities. I mean, if this function gives you anything other than plus or minus I on this input, then obviously it's wrong. But either of those 2 inputs seems correct. Nothing wrong with that. And so maybe this student's functional does compute a square root of the identity, which is not very impressive, really. But what we do with it now is we say, okay, the nature of these oracle computations is that the functional said, okay, I maps to whichever, after looking at only finitely much of its oracle. So it looked at the identity up to one of those fields, kn, and no further. And the functional somehow said, okay, when I see that my input is the identity on kn, I'm going to output I maps to I, or whichever it outputted. Now we say, okay, back to this student. Now I want to run the same functional on another square. Which one? Well, I'm going to come up with a nasty square here. In fact, 2 squares. So here's an f and an h. They are both squares in the Galois group. The f has the property that it's the identity on kn, so different f's for different n's here, right? Whatever kn was, there is an f which is the identity on kn, and then, so the f and the h both do that. But the f has the property, it does have square roots, but all of them map I to I. And the h has the property, it does have square roots, but all of them map I to negative I. And so if the student's functional said map I to I, I'm going to give it one of these h's. And on that oracle, h, well, h again is the identity up to kn, so the student's functional is going to output I maps to I, just like it did before. But that's wrong. There are square roots, but they all map I to negative I. And of course, conversely, if the student's functional mapped I to negative I, I'm going to run it on this f, and it'll be wrong there. Right? So somehow or other, the functional messes up on something. Okay? As far as what are these f's and these h's, I'll tell you, the first paragraph tells you about the f, right? Yes. Actually, the first paragraph tells you about an f, yes, which has square roots have to map I to I. To get the f, pick a prime so large that the kn doesn't have anything to do with this prime yet, square roots of it or anything like that. Kn may well contain the identity. What I'm interested in is the splitting field of the fourth root of the prime. The identity might already be in Kn, but the rest of that field will not be. So they're linearly disjoint over Q of I, and which means the Galois group is a direct product. And in this Galois group, there are two squares. The identity is one. The other is the square of the 4 cycle on the square roots of, right? The Galois group is the dihedral group of the square. So the 90-degree rotation of the square squares to this, and so does the 90-degree rotation the other way. And nothing else squares to that. And both of those 90-degree rotations have the property that they force you to map I, well, they're automorphisms. They map I to I. So if I extend my identity by saying, okay, on this new field that I haven't told you about yet, my f maps, what is it? It interchanges the two real fourth roots of p, and it interchanges the two complex ones, the two imaginary ones. Then that's exactly the sort of f we want. The trick for h is the same thing, except not with square roots of fourth roots of primes. It just uses a Galois group S4, and it goes very much the same way. Time is short, so I'm not going to run through all of that. What I do want to point out, though, is that it's good to think about this actually as a topological thing. So here's what happened. For each n, we said we could do this. So for n equals 1, we computed an f1 and an h1 that both are the identity on k1, and then have this property about all of their square roots map I to I, or all of the square roots of this one map I to negative I. For n equals 2, 3, 4, we computed another f and another h. So f1, f2, f3, and so on up. The f's converge to the identity, right? So do the h's. And basic fact about computable functions, I mean, I said up here on Cantor space, which is essentially what you're dealing with the Galois group, of course. Computable functions are continuous in the normal topology on Cantor space. And I'd be delighted to sit and show that to anybody who's surprised by it or hasn't seen it before, but not right now. What that means, though, is if you're trying to compute a Skolem function here, you're in a spot, right? Compute the Skolem function on the identity. Well, there's this one sequence that converges to the identity, and its square roots always map I to negative I. There's this other sequence that converges to the identity, square roots always map I to I. What's a poor Skolem function to do, right? I mean, you're stuck. Okay, so in fact, there can't be any continuous Skolem function. For computability, that's the same as saying, even if you were given some fixed oracle, like the halting problem or something, you still couldn't compute square roots. You still couldn't compute a Skolem function for this. Okay, with that, I definitely wanted to get through that, and we should wrap up. A few cool things. The fact that the square roots are the paths through a tree like this means that if let's say f was computable, there will always be a square root of low Turing degree. Okay, and that relativizes. Whatever f was, there will always be a square root that it has Turing degree low relative to the degree of f, which means that you actually can get, okay, so back up for just a second. The basic question about gal 0 of q, is it an elementary subgroup of gal of q? We don't know that yet. We know we can't uniformly compute square roots, but there might, I would guess you can't, that there's a computable square with no computable square root, but I don't know that. Right? Okay, but if you take what's called a Scott ideal, which sort of means you can close under taking paths through finite branching trees, then you do get a countable dense subgroup, nice subgroup, that's elementary at least for existential and universal formulas, and it turns out, in fact, it's elementary for all positive formulas about the Galois group. Negation is the devil here. Negation makes things nasty. Okay, but for positive things, it's very nice. There are a few more slides. I'm just going to think, I want to ask the same general question that I was doing before. When you have a definable subset, what is the arithmetic complexity? Right? We said for existential formulas, it's at most sigma 02. For EA formulas, I don't know whether it's sigma 02 or sigma 03, or maybe it could be as hard as sigma 11. It could jump way up to, out of the arithmetical hierarchy at that point. Don't know that yet. So there's a lot of room for questioning there. The existence of these so-called decisive extensions is a very cool thing. It made me think even a little bit about Hilbert's 10th problem for the rationals. I'll mention that to anybody who's interested. There was work by Sasha Shlapentokh and Jennifer Park that's relevant to that. I think what I'll do is leave up here for those who are interested from any old angle, topics for further study. Some of this is aimed at computable structure theorists, some of it at number theorists more generally. More generally, yes, okay. And yeah, it is time to wrap up. I would love to take questions. Thank you very much.